We have discussed in very detail in the previous two lectures on damped harmonic oscillator the basic theory of damped harmonic oscillations. And in the beginning of the first lecture on this damped harmonic oscillator, I have told you that this damped harmonic oscillation is different from the free oscillation in a particular manner. In case of free oscillation, there is no loss of energy of the oscillator. It means you can say that the total mechanical energy, that is the sum of the kinetic and potential energy of a free oscillator, remains constant. It does not change with time. But the situation in case of damped harmonic oscillator is different. In this case, as you know, a resistive force acts on the oscillator, and due to that dissipative force, the energy of the oscillator does not remain constant, but it decreases with time. And that's why, since energy is not constant, it decreases with time, or you can say that energy gets lost, so that the amplitude of oscillation also decreases exponentially with time. And finally, this oscillation gets stopped. So this is a very important and a key problem to discuss how the energy decreases with time in this case. In other words, we can say we must see what is the power dissipation in case of damped harmonic oscillator. So in this third lecture on this damped harmonic oscillation, our aim is to discuss the important problem of power dissipation, and along with it we will also discuss the relaxation time and quality factor. So the basic aim of this lecture is to relate the power dissipation, relaxation time and quality factor. What are these quantities and how they are related? This is the aim of this lecture. And so it is a very important problem of damped harmonic oscillation. Okay. So now let us start to know about these things which I have just explained. Okay. Let us consider there is an oscillator. When you say oscillator, actually oscillator may be an electrical oscillator, a quantum oscillator, but as you know, we are dealing here the problem of mechanical oscillator. So whenever I say oscillator, you think about the mechanical oscillator, and you can think that there is a particle which acts like an oscillator. Okay. And that particle or that system, or you can say that oscillator, is oscillating in a viscous medium, or you can say a resistive medium, about its equilibrium position O. Okay. And during its oscillation at any moment t, let us consider that the particle or the system or the oscillator is at this point P, when its displacement from its equilibrium position O is x, as I have shown in this figure. Okay. Now what is this x? You have obtained the value of x by solving the equation of damped harmonic oscillation in the previous lecture. So here I will write directly the expression for x which we have obtained in the previous lecture. As you have seen that actually the particle oscillates simple harmonically, but not this is free simple harmonic motion, but damped simple harmonic motion in which the amplitude of the oscillation decreases exponentially with time, but the motion is simple harmonic. So we have seen in the previous lecture that this x of t, which represents the displacement of our oscillator at any moment t, that was obtained earlier, that it is equal to a sine omega t plus phi. And I hope you have an idea of all the quantities used in this equation because you have already learned these things in the previous lecture. As you have seen that this A, which is amplitude of the oscillation, this is not constant, but it is equal to A naught e to the power minus bt, and you can see that actually this amplitude is decaying with time t exponentially or asymptotically. So this, when you will plot a graph of A of t in against of t, you know the form of this graph will be like this. Its maximum value, that is the value of A at t equal to 0, is A naught, and as the time passes this amplitude decreases exponentially. Okay, and this omega is the frequency of this damped harmonic oscillator, and this frequency you have seen earlier is given by a square root of omega naught square minus b square, where you know omega naught is what? Can you say? Definitely you can say, if you have watched my previous video, that this is nothing, this is simply the natural frequency of our oscillator. Okay, and this b is damping coefficient. Okay, so when this damping coefficient will be 0, that is if you will consider the free oscillation, then this omega will be simply equal to omega naught. But in this case, due to the presence of damping, the frequency of oscillation of our oscillator is not equal to its natural frequency, but it is less than the natural frequency. Okay, and this b was defined earlier as r divided by 2m, where m is the mass of the oscillator or the system, and r, you know, this is actually called what? This is a resistive constant. This depends on the nature of the medium. Okay, in case of non-resistive medium, this r is 0, and when r will be 0, certainly this b will be 0. Okay, so you can write the expression for x of t like this. This is A naught e to the power minus bt times sine omega t plus phi. Okay, this is the displacement of our oscillator at any moment t from its equilibrium position. Now, as our aim is first of all to discuss what will be the energy of this oscillator at any time t. You know, the energy of a free oscillator at any moment is constant, and that is equal to half m omega square a square. And in that case, actually this a is constant, omega is the natural frequency in that case. But here you will see that this energy will be not constant. So first of all, our aim is to derive the expression for energy of this oscillator at any moment t. And when you say energy, it means mechanical energy, which is sum of the kinetic and potential energy. So getting the value of kinetic energy, you must find the velocity of the oscillator at any moment t. So first of all, I am going to find the value of velocity of the oscillator at any time t. And you know, if its velocity at any time t is v of t, then this is defined by dx by dt. Okay. Now let us substitute the value of x of t, which I have defined in this equation 1. Since a naught is a constant factor, so this will be outside of the operator, and so v of t is equal to a naught times d dt operated on e to the power minus bt times sine omega t plus phi. Okay. Now you have to differentiate the product of two functions. The first one is the exponential function e to the power minus bt, and the second one is the trigonometric function sine omega t plus phi. So you must apply the rule of the differentiation of product of two functions, which we have studied in your course on calculus. So first of all, we will differentiate the first factor, keeping the second factor at h. So you know, the derivative of this e to the power minus bt with respect to t, what will be that? That will be minus b times e to the power minus bt. And the second factor, sine omega t plus phi, has been kept constant, has been kept at ease. Okay. Now we will differentiate the second factor and keep the first factor at ease. And you know the second factor is sine omega t plus phi, where phi is constant. And its derivative will be what? Its derivative will be omega times cos omega t plus phi. So the second term will be omega e to the power minus bt times cos omega t plus phi. This is a very simple differentiation. Okay. Now you can see that this exponential factor e to the power minus bt is in both terms, so we can take it as a common factor. And so you can say that this v of t will be equal to a naught times e to the power minus bt times omega cos omega t plus phi. I have actually written the second term here at the place of first term. And the first term is what? This is minus b times sine omega t plus phi. Okay. So this is the velocity of our system at any time t. Now getting the value of velocity, we can easily find the kinetic energy of the oscillator. And its potential energy is due to the restoring force, which have the form half kx square, as you have seen earlier. Okay. So the total mechanical energy, which will be the sum of kinetic and potential energy, now we can find easily. You know, the total mechanical energy E is the sum of kinetic energy and potential energy. And kinetic energy, you know, this is the classical expression for kinetic energy, half mv square. And the expression for potential energy, you know, is half kx square. Okay. These are the well-known expressions for the kinetic and potential energy of the oscillator. Now let us substitute the values of v and x in this equation. As you can see, the value of v we have obtained in this equation too. So when we will square this v, what will be your result? That will be simply a naught square e to the power minus 2bt. Okay. And the square of this bracketed term, that is omega cos omega t plus phi minus b sine omega t plus phi, this will be simplified by using the formula of a minus b whole square. That will be a square plus b square minus 2ab. So using that very formula, the term inside the bracket will be what? A square. At the place of a square, we will write omega square cos square omega t plus phi. And at the place of b square, we will write b square sine square omega t plus phi. And minus 2ab, and that will be minus 2 omega b cos omega t plus phi times sine omega t plus phi. Okay. And now the second term, this is half kx square. Okay. So here you can see this is half k, and x, you know, x is given by this formula, which I have written in this equation 1. So after squaring x, you will get a naught square e to the power minus 2bt times sine square omega t plus phi. So I have written it here, you can see. Okay. Now we consider a limiting condition. As you know, oscillation takes place only when we consider the case of low damping. In case of over damping and critical damping, you have seen earlier in the basic theory of this damped harmonic oscillation, no oscillation takes place. Our system oscillates only when you consider that damping is low. When you say damping is low, that means damping coefficient B is much smaller than this natural frequency omega naught. And if you consider that B is much smaller than omega naught, it means you are saying that this B is very small. And mathematically you can say if B is very small, it means B is tending towards 0. So in the RHS of equation 3, the terms containing b or b square can be neglected. So we will neglect this term b square sine square omega t plus phi, because here you get a b square factor and this b square is tending towards 0. So this term will be much smaller than the remaining terms. And similarly, the third term also contains this b here, so we will also neglect it. So neglecting the terms containing b and b square, the only two terms remain in the RHS. And in this condition, you can also see, since we are neglecting b square in comparison to omega naught square, so as omega square is equal to omega naught square minus b square, so after neglecting this b square in comparison to omega naught square, this will be almost equal to omega naught square. And you know, omega naught square is equal to k over m, where k is the force constant. So under these limiting conditions, what will be the result for E? Actually, in this condition, you can see the frequency of oscillation of our damped harmonic oscillator is almost equal to its natural frequency. Almost equal. Not exactly equal, but almost equal. So in this extreme condition, we will now simplify the expression for total energy E, which I have obtained in equation 3. So the second term inside this square bracket and the third term will be neglected, and at the place of this omega, now we will write omega naught. Okay, and so you can see this equation 3 will be now written like this: E equal to, see here, half m a naught square e to the power minus 2bt times this omega square cos square omega t plus phi. But omega is now almost equal to omega naught, so I have written here omega naught. Okay, and the last term is what? This is half k a naught square e to the power minus 2bt times sine square omega t plus phi. Okay, sine square omega t plus phi. Now here this omega naught square, you know, is equal to k over m. So omega naught square has been replaced by k over m, and so this m and this m will cancel out. Okay, this will cancel out. Okay, and now you can see that the factor half a naught square e to the power minus 2bt times k is a common factor. This is present in both terms. So let us take half k a naught square e to the power minus 2bt as a common factor and simplify the result. So you can see E will be now written as half k a naught square e to the power minus 2bt times cos square omega t plus phi plus sine square omega t plus phi. But you know, this cos square omega t plus phi plus sine square omega t plus phi, it is equal to 1. And since it is 1, so the expression for energy will be what? This will be half k a naught square e to the power minus 2bt. This is the expression for the total mechanical energy of a damped harmonic oscillator. Now, the presence of this exponential factor e to the power minus bt, what implies this factor? You can see that due to the presence of this very factor, it is obvious that the total mechanical energy of our oscillator is not constant. It is time dependent. And how it varies with time? You can easily see that this energy decays, this energy decreases with time exponentially. Okay? So after a very long time, energy of the oscillator will completely ceased. It will be energy less or powerless. You can see If we are talking about the initial moment, that is the moment when the oscillation just has been started, we take that time t equal to 0. So in the beginning, when t was 0, what was the energy of our oscillator? When you will take t equal to 0, this factor e to the power, e to the power, the page has been turned. You can see, taking t equal to 0, e to the power minus 2bt. This will be e to the power 0 and this is 1. And so, energy at the initial moment of this oscillator will be what? This is E equal to half Ka naught square, because this exponential factor is now 1. And we consider that this half Ka naught square is the energy of the oscillator in the beginning when it just starts oscillation. Okay? And we denote this initial energy by the symbol E naught. Okay? In fact, this is the maximum energy of our oscillator, because energy is decreasing with time. So at the initial moment, its energy was maximum. Okay? And if we consider an extreme condition that this time is tending towards infinity, what will happen to this energy? You can see, when t will tend to infinity, you can see this factor e to the power minus 2bt, this will tend to e to the power minus infinity, and e to the power minus infinity, you know, this is 0. So after a very long time, the energy of the oscillator will be 0, and when the energy will be 0, the oscillation will stop. Okay? So in the basic theory of this damped harmonic oscillation, I have told you that in case of damped harmonic oscillator, since the energy decreases with time, so finally the oscillation gets stopped. Okay? Now, in terms of this E naught, which is the initial energy of our oscillator or maximum energy of oscillator, the expression for the energy of the oscillator, which I have defined in this equation 4, can be written like this. At the place of half Ka naught square, you can now write E naught. So E is the energy at any moment t. So energy of the oscillator at any time t is given as E naught times e to the power minus 2bt. Okay? And it is obvious from this result that this energy is not constant, but it decreases exponentially or asymptotically with time t. I have shown in this adjacent figure how this energy varies with time t. You can see when time t is 0, then energy is E naught, and this is its maximum value. But as the time passes, energy decreases, energy decays exponentially, and when t tends to infinity, then E tends to 0. So finally this curve has been shown parallel to time axis, which implies that this energy will be 0 when t will tend to infinity. So never intersect the time axis by this curve at a finite value. Okay? So I think we have clearly understand what is the energy of our damped oscillator at any moment t, and how it is related to time, how it decays with time. Okay? This is a very interesting concept. Okay? Now you can see, if we consider that our oscillator is a free oscillator, it means you are considering an undamped oscillation. When you say undamped oscillation, that means we are considering that our oscillator is oscillating in a medium which does not impose or exert any resistive force on the oscillator. In that condition, this damping coefficient will be 0. And if the damping coefficient is 0, what will be the energy? Energy will be simply equal to E naught. It means energy of the oscillator will not change, it will remain constant. And already we have discussed these things in the case in the lecture on free vibration of my playlist. Okay? Now, after getting the value of energy and knowing how it decreases with time, now you can easily find the uh, a very important quantity which is called relaxation time. So first of all, we will see how this relaxation time is defined, and then we will obtain the expression for it. Actually, this relaxation time is defined as a time interval during which the energy of our damped harmonic oscillator decays to 1 over t times of its initial value, that is the value at t equal to 0. It means you have to find out the value of time t in which the energy of the oscillator, which was initially E naught, becomes E naught by E, 1 by E times E naught. So according to this definition, if we take t equal to tau, where tau represents the relaxation time, then according to the definition, energy of the oscillator at this time tau will become E naught over E. Okay. Now, if you want to find the value of this tau or expression for this tau, you can easily find it. How? In fact, we will substitute the value of this condition, not value, this condition in this expression for energy. You can see this expression. When you will take t equal to tau in this expression, according to definition, this energy E will be equal to E naught by E. So, replacing this E by E small e, which is exponential, and this t by tau, we can obtain the expression for the relaxation time. So you can see I have written here E naught over E is equal to E naught times e to the power minus 2b tau. Tau is the relaxation time. Okay. Now this E naught and E naught will cancel out, and so 1 over E, this will be equal to what? This is e to the power minus b 2b tau, and therefore you can write e to the power 2b tau will be equal to E. Okay, and so what will be this 2b tau? You know, if e to the power x is y, then x is what? This is ln y. So here this 2b tau, this will be equal to ln e, but ln e you know is equal to 1. So 2b times tau is equal to 1, and therefore you can say that relaxation time is 1 over 2b. And this is the expression for the relaxation time. Okay, this is the expression. And you can see from this relation that actually this relaxation times depends on the damping coefficient B. Actually, relaxation time is inversely proportional to the damping coefficient. So if the damping coefficient is small, then tau will be large. And if damping coefficient is large, tau will be small. And as you know, in case of free oscillation, this damping coefficient is least, it is equal to 0, and in that condition, this relaxation time will be equal to infinite. Okay. It means relaxation times becomes undefined when we talk about the free oscillation. So you can remember when we were discussing the problem of free oscillation in my previous videos, I have never talked about this relaxation time. Why? Because in that condition it is not a defined quantity, and it has no meaning in that condition. And so in case of free oscillation, we have never talked about this relaxation time. But whenever you will talk about the damped harmonic oscillation, this will be a very significant quantity. Okay. So I think you have clearly understand what is this relaxation time, what is expression for it, what is the factor on which it depends. Okay. Now, after getting the idea of total mechanical energy of a damped harmonic oscillator and this relaxation time, now you can easily understand the power dissipation of the damped harmonic oscillator. As you have seen that energy of the oscillator is decreasing with time, it means there is a loss of power of the oscillator. And that's why when the oscillator becomes completely powerless, oscillations stops. You know, power is what? This is actually the rate of change of energy. This is called power. Here there is a loss of energy, so there will be loss of power, or there will be a dissipation of power. So actually, in a very simple way, we define the power dissipation as the rate at which energy of the oscillator gets dissipated. It means the loss of energy of the oscillator in 1 second, that is called power dissipation. Now, if you consider that in time dt, the loss of energy is dE, then in 1 second, the loss of energy will be dE by dt, and this will be the power loss. But since energy is a decreasing function here, E decreases with time t. So in definition, to get the correct expression mathematically, we have to put this minus sign. Minus sign. Why minus sign? Because E is a decreasing function. If you will not put this minus sign here, then P will be obtained negative. But power cannot be negative. So for get rid to that minus sign in definition, we take P equal to minus dE by dt. So you can say that this minus sign here in this definition only implies that energy is decreasing with time t, or energy is a decreasing function of t, so that the rate of decrease is written by minus dE by dt. Okay, minus dE by dt. Now, if your aim is to find the expression for this P, you can easily find by this definition. As you know, E is given by this much. E is equal to E naught times exponential to the power minus 2 beta. So let us put here this value of E. Since E naught is a constant term, so P will be written as minus E naught d dt e to the power minus 2 bt. Now, the derivative of this e to the power minus 2 bt with respect to t will be what? That will be minus 2b times e to the power minus 2 bt. And that minus and this minus will become plus, and your result will be p equal to 2b e naught times exponential to the power minus 2 bt. Okay. But let us see this part of the expression, E naught times e to the power minus 2 bt. You can see E naught to the power minus 2 bt, this is simply equal to E. So instead of this factor, we can write E, and so that the expression for power dissipation is equal to 2be. Okay. So you can see that this power dissipation is also related to the damping coefficient B. And as in case of free oscillation, this damping coefficient is 0, and so P will be 0. So it is obvious, as you have learnt earlier, that in case of free oscillation, there is no loss of power of the oscillator. Power of the oscillator remains constant, and once a free oscillator starts oscillation, it continues its oscillation for infinite time because there is no loss of power. Okay, but in a damped medium, since B will be not 0, so there will be a power loss, and finally this power will become 0 and the oscillation will stop. Okay. Now, you have learnt about the two quantities, power dissipation P and the relaxation time tau. Now, we will see how these two quantities are related. In other words, you can say that how we can express the power dissipation in terms of the relaxation time. This can be done very easily. Just you have seen in this equation 7 that the dissipated power by the oscillator is P equal to 2BE. Okay, but this damping coefficient 2B is related to the relaxation time, as you have learnt here in this equation 6. Tau is equal to 1 over 2B. So this 2B will be equal to what? This will be 1 over tau. So in that very equation, 2B can be replaced by 1 over tau. So you can see I have written it here that 2B is equal to 1 over tau. So now let us put this value of 2B in this equation, and so you can say that this dissipated power P is equal to simply E over tau. So you can say that power dissipation in this case of damped harmonic oscillator is simply the ratio of the mechanical energy of the oscillator and the relaxation time. Okay, this is a very important relation, and these relations are very important for your objective questions. Okay. Now, after getting the idea of energy of a damped harmonic oscillator, power dissipation, relaxation time, finally in this lecture we are going to see a very important parameter which is called quality factor. Actually, whenever you discuss the case of oscillation, we always talk about the quality factor. In case of electrical oscillation in AC circuit, or in case of mechanical oscillation here, we will also see this quality factor when we will discuss the forced vibration. Okay, but at different places the definition of this quality factor is different, but meaning is same. Physical meaning of quality factor remains same when you discuss any type of oscillation. Okay, but in a particular situation its definition is it is defined in a particular manner. Here quality factor we will define in case of a damped harmonic oscillator. So how this quality factor is defined in case of damped harmonic oscillator, let us see the definition first. Actually, this quality factor is defined as 2 pi times of the ratio of energy stored in the system to the energy lost per period. This is a very remarkable fact, per period. It means your definition says that if you have to find quality factor, how you can obtain it? You have to find a ratio of what? You have to find the ratio of energy stored in your system and the loss of energy by your system in one time period, in an interval equal to the time period of the oscillator. And after that you have to multiply it by the factor 2 pi. Then you will get the quality factor. So remember this definition, quality factor, but remember this definition will be used only when you are talking about the damped harmonic oscillation. You can't use this definition if you are talking about the LC oscillation or the oscillation in case of LCR circuit, in case of resonance, in case of forced vibration. You can't use this definition. This is a particular definition which is fit in case of the damped harmonic oscillation. Okay. So remember this definition, Q is defined as 2 pi times energy stored in the system divided by loss of energy of the system in one time period. Okay. Now you know, if E be the energy of our system, then the loss of energy per second is given by dE by dt. You have been surprised that why I have not written here P equal to minus dE by dt. Why I have not written it? Because I have not written this minus sign because I am already telling that this is energy loss. We are talking about loss. For example, if a person says to you that I have sold my fruits and I have a loss of 200 rupees. When he says a loss of 200 rupees, he never says a loss of minus 200 rupees. But he can say that today I have a gain of minus 200 rupees. He can say. When the person says that he has sold his fruits and has a gain of or a profit of minus 200 rupees, that means the person has no profit but he has lost 200 rupees. So if you say lost, then there is no need to put the minus sign. So I have not put it here minus sign. Okay. P equal to d by dt. Now, energy lost per second. You have seen that energy lost in 1 second is equal to dE by dt, and that is equal to P. That is simply the power dissipation. So you can say in 1 second, what is the loss of energy? Loss of energy in 1 second is equal to P. So loss of energy in t second, where t is the time period, what will be that? That will be simply Pt by unitary method. Okay. So energy loss per period is equal to Pt. Okay. And energy stored in the system at any moment is T. So according to this definition, you can now say that quality factor will be 2 pi times E divided by Pt. Have you understand or not? E is the energy stored in the oscillator at any moment T. And Pt, this is loss of energy of the oscillator in an interval equal to the time period of the oscillator. Okay. But this E is related to the relaxation time. As you know, you have seen earlier that this P is equal to E over tau. Okay. And so you can say that E is equal to P tau. So now let us replace the factor E in the numerator of equation 9 by P tau. So after replacing it, the expression for Q will be what? This will be 2 pi times P tau divided by Pt. Here this P and P will cancel out, and the quality factor is 2 pi over T times tau. Okay. But you know 2 pi over T, T is the time period. So this 2 pi over T, you can say this is the cyclic frequency or angular frequency of our oscillator. And we have assumed that our oscillator is oscillating with a frequency omega. So at the place of this 2 pi by T, now you can write omega. So finally we get the quality factor of this damped oscillator is Q equal to omega times tau. Omega times tau. Okay. But this tau, you know, is related to the damping coefficient by this relation you have just learnt. And therefore, in this expression for Q, you can replace this tau by 1 over 2b. So finally, we get the quality factor is equal to omega divided by 2b. So this quality factor depends on the value of the damping coefficient. It is actually inversely proportional to the damping coefficient you can see. So if B will be large, quality factor will be small. But when B is small, quality factor will be large. So in case of low damping, there will be a high quality oscillation. So this is actually the measure of the quality of damped oscillation. So to get a high quality damped oscillation, the damping of the medium must be very small. Okay. But if you now think about what will be the quality factor of this free oscillation. You know, in case of free oscillation, the damping coefficient is 0. And this is actually the lowest value of the damping coefficient. And so quality factor will be infinite. So the maximum quality factor you get in case of what? In case of free oscillation. But in case of damped oscillation, this quality factor will have some finite value. Okay. But if you think about a damping medium, a resistive medium whose damping coefficient is very small, in fact, in that condition, the oscillation is almost as a free oscillation, and so that the uh, quality factor is very high. So this was a very interesting lecture, I think, and you have clearly understand all the steps, all the concepts. And now, after this, there will be only one lecture on this damped oscillation, and except some numerical problems. We will discuss some numerical problems based on it in the in the next lecture. But in the second lecture, in continuation, we will discuss a very important uh, quantity regarding this damped oscillation, that is called logarithmic decrement. Okay, so definitely you should wait for my second lecture on this regarding the logarithmic decrement. Okay, thank you very much.